So this is a continuation of our previous video. We're going to do another worked example. This time, the problem is going to involve damping, and so the math is going to be a little messier, particularly when it comes to solving for the constants. But we're going to go through the entire process of finding the constants and then solving the problem. So in this example, a spring is stretched 6 inches by a mass that weighs 8 pounds. And this is in English units. The mass is attached to a dashpot mechanism that has a damping constant of 0.25 pounds per second per foot, seconds per foot. Again, don't worry about the units because that's taken care of. They're specifically set up to match with the reciprocal of the velocity to produce force, and is acted on by an external force of 4 cosine 2t. So first thing is we have to find the mass for the equation. So we're going to convert 8 pounds to mass, and that's going to give us 8 divided by gravity is 1/4 of a slug. The damping constant is provided directly as 0.25 or 1/4. And then the spring constant is calculated from the fact that it takes 8 pounds to stretch the spring 6 inches. And when you set 8 equal to the force, and then you divide by half a foot, you get K is equal to 16. So our equation then is going to become the 1/4 y double prime plus from the slugs 1/4 y prime from the 0.25 damping constant, 16 from the spring constant, and then our forcing of 4 cosine 2t. Now, if you have to eliminate the fractions in order to make the problem easier to work with, you need to do it after you set up your whole equation, because if you rescale this side of the equation, you also have to rescale the forcing function. All right, so first things first, we're going to solve for the characteristic equation, which would be r squared plus r plus 64 is equal to 0. And this doesn't factor in any obvious way because 64 does not have factors that add to 1. And so we're going to use the quadratic formula. And when we plug that into the equation, we end up with 1 minus 256, which is obviously negative. And so we get this complex solution. In many real world problems, you are going to get appallingly hideous coefficients and constants, and that's just life. The process is the same, but you are going to end up with messy math. So our lambda plus or minus mu I, the lambda is going to be -1/2, and the mu is going to be the square root of 255 over 2. I is in the formula already. This is underdamped because the solution is complex, which means it's going to oscillate like one without damping, but the amplitude is going to decrease over time. Now we are going to take this lambda component and put it in the e. So this will be e to the lambda t, so e to the -1/2 t. And then the complex term, the mu component, goes inside of our trig functions, a cosine square root of 255 over 2 and b sine square root of 255 over 2. So this is the homogeneous solution. And so then we need to deal with the forcing term. And we need to deal, and I should stress this, generally we want to deal with the forcing term before we attempt to solve for a and b. So our frequency of the forcing term was 2t, and that is not the same as the one from our homogeneous solution. So our ansatz, our guess for this forcing term, is going to be some constant times cosine 2t, and then some other constant times sine of 2t. We need to take our two derivatives. The first derivative, 2, change the sign, -2c sine 2t, and then 2d cosine 2t. Take the second derivative, another 2 comes out, this turns sine into cosine, and then another 2 comes out, and cosine turns into negative sine. And then we plug these and the original y into our equation. Y double prime, we replace this. Y prime, we replace this. And then the original guess goes in here as 64y. And it looks like I dropped the coefficient. So you're going to, and the answer here is now wrong. That makes me depressed. But you would multiply by the 64 by these two, and then set it equal to your forcing term. And what you're going to do is you're going to collect your terms, the ones for cosine and the ones for sine, and then you're going to set your coefficients equal to each other. And from there, solve for C and D, which of course these two are not quite correct because I dropped the 64. But that is the general process. You have your homogeneous solution, and whatever you solve for these forcing terms, that becomes the steady state solution. Because this part of your equation is decaying, that will be your transient solution. These are not decaying. This is based on that forcing. And so that's going to remain forever. But again, at this point, then, after fixing these constants, then it would be safe to solve for your A and your B.